Now, I hope you can see the screen on gas absorption and desorption. Now, another term for stripping is desorption. It's actually the opposite of gas absorption. So we will go to the definition of these unitary processes later. Now, actually, the fundamentals or the principles that we will be using with gas absorption, of course, with the exception of the design part, is anchored upon phase equilibria. So the reason why you see the next slide, which is labeled as phase equilibria. So we're going to have a little review of the phase equilibrium or equilibria that we have discussed in our module 1. So in phase equilibria, we have to think of, I'll have this projected. So we have to think of that mass transfer ceases when equilibrium between the two phases is already reached. So mass transfer stops whenever equilibrium is reached. That is why it is actually the turning point for this particular process, because once equilibrium is reached, there isn't any more separation of one particular component from one phase being transferred to another. Now, the rate of this mass transfer is directly proportional to the driving force, and this driving force is that particular condition when we already depart from what we call equilibrium or stable condition. So once equilibrium is not yet reached, we still have enough driving force that will fuel mass transfer. Okay, so this rate of mass transfer, how fast is it, would be proportional to the, of course, the driving force. In this case, our driving force will be the difference in the concentration of the component that is to be transferred from one phase to another. So the greater the amount of the component from a phase in which it's going to be taken from, the greater is the rate of mass transfer. But this mass transfer ceases when equilibrium is already reached. Now, to be able to evaluate the rate of mass transfer, the driving force has to be accurately determined, which will in turn rely on the equilibrium between the phases. Okay, so that is why it's anchored upon the concept of equilibrium. So I will just proceed. Just let me know if it's not transitioning. Now, in nearly all situations, two phases are involved except the solid phase. So when we speak of phase equilibrium, and the controlling variables, it's not transitioning. It's okay. So the controlling variables, which you have learned when we discussed the topic of phase equilibrium, are temperature, pressure, and concentration. And the equilibrium data can be taken from tables or graphs and can even be calculated through the use of equations, which are also shown to you. So we'll not go back to that. Now, for most operations, however, the pertinent equilibrium relationships are shown graphically. So that is why you have graphs to extract the relationship between X and Y for a particular system that is specified or stated in the problem. Now, what are the bases for equilibrium? So a short review again, we have the phase rule, wherein we determine the variance, the F, or the number of degrees of freedom, so otherwise known as the variance. So it is computed based on this formula, the number of components minus the number of phases plus 2. Okay. Now, this degrees of freedom tells you the number of independent intensive variables. So these intensive variables that we can have, that we will have to look into, will be the temperature, pressure, and concentration. So the number of intensive variables, which is calculated from the degrees of freedom or variance, or that's the F, is the number of variables that needs to be fixed. So to define the equilibrium state of your system. So if you were done, the number of variance variables are fixed, an infinite number of states fits the assumption, while if F is too many, your system is said to be overspecified. Now, normally, since we will be dealing with two-phase systems here, For a two-phase systems or a system that contains two components, variance is equal to 2, which is also equal to the number of components. So if, for example, pressure is fixed, the liquid phase concentration can be changed independently, then the gas phase composition and temperature, in the case of gas absorption, which is governed by liquid-gas equilibria, can be determined. So in most cases in here, class, the problem will give you two intensive variables, temperature pressure or temperature concentration. That way you'll be able to determine what the problem requires. Otherwise, since our number of phases, our number of components corresponds to our variance, we won't be able to determine what the problem will require us to determine. Now let's look at a quick look at Rayos Law again. So Rayos Law, which is applicable only for ideal system, tells you that the partial pressure of gas A in the gas mixture is equal to the product of its vapor pressure, pure vapor pressure, that is multiplied to its mole fraction in the liquid phase. So you have here XA and P sub A. So XA meaning the mole fraction of A in the liquid phase. If it's mole fraction of A in the gas phase, we simply change this to Y. Okay, so that's for Rayos Law. And since oftentimes our systems are not ideal, so we have another equation to use, and that's Henry's law. And here you have the Henry's constant. This law also still determines the partial pressure of A in the gas phase, just like your Rayos Law. However, in here, instead of the pure vapor pressure of A, which is multiplied to its mole fraction in the liquid phase, in Henry's law, it would be the Henry's constant. Now, from this Henry's law, we can have another formula, or we can derive the formula relating the mole fraction of A in the gas phase to the mole fraction of A in the liquid phase. We just need to divide the equation, the provided equation here, by the total pressure of the system. Oftentimes, it's also equal to the atmospheric pressure, even if the problem does not specify it. So it's automatic that your total pressure is the atmospheric pressure. So this is your alternative equation to use if your system is non-ideal. Now, we also discussed in part about the the K factor, or the distribution coefficient. Now, which is the ratio of the mole fraction in the vapor and the liquid phases of a particular component, if we base it on a particular component, I, in this case, at equilibrium. So the condition is at equilibrium. What is the ratio of this mole fraction? So Y to X at equilibrium, speaking of the same component. Now, if Rayos Law and Dalton's law is applicable for our system, meaning it's ideal, then we have an alternative equation here to use. The P sub I prime is the pure vapor pressure of component I divided by the total pressure of the system. That would be the K sub I, the distribution coefficient, or the K factor. Now, another measure of equilibrium is the relative volatility, or the alpha. So if Rayos Law holds, the ratio of the K factors and the relative volatilities of the components are the same. So let's say in this case, I like to project again, In this case, you are given the relative volatility of I, component I, with respect to component J for a system that has components I and J. So you could see here that you can get the distribution coefficient in terms of I and divide it with the distribution coefficient in terms of J, which you can determine based on the two formulas that you can choose from. It's either in terms of mole fraction ratios or in terms of pure vapor pressure and total pressure ratio. Okay. Now, this relative volatility can also be, as given here, the pure vapor pressure of component I ratio with the pure vapor pressure of component J. So these K factors are strongly temperature dependent, but relative values of K for two-component system changes only moderately. So that is why the systems that are given you are limited only to two-component systems, because the variation of K with respect to temperature is not noticeable. So it is negligible. So that is why it's like that. Now, these are the different equilibrium diagrams that we can get the relationship between X and Y, or between X and P, partial pressure, or in this case, X and Y with respect to T. Okay, this was shown to you as well. The equilibrium relationship can also be taken from the table. Okay, given the temperature, you'll be able to tell what would be the corresponding mole fraction of a particular component, both in the liquid and in the vapor phases. This is much easier actually than the graph, because you can read it out in here. Though the relationship between, I would like to emphasize again, though the relationship here is not linear at all times, then if the particular temperature that is given is not amongst the temperature in this column, you can approximate by using interpolation. Okay, that way you can find whatever it is that you need, whether it's vapor pressure or mole fraction from the table. Now, for the mole fraction problem, so let's say, for example, anyways, this has a solution, and they have, I think this was already discussed partly. I gave you sample problems on this under phase equilibrium. So we will just skip this sample problem number 1. Anyway, this is just substitution to the formula or to Henry's law. Okay. Now, for sample problem number 2, you are to determine in here the partial pressure of CO2 that must be kept so that your CO2 will not vaporize from your aqueous solution. If I'm not mistaken, this was also given in the slide on phase equilibria or in equilibrium, but it's still in here, so you just have to review again. Now, in here, we'll have to determine the relative volatility of benzene-toluene system at 90 degrees Celsius and 100 degrees Celsius. Now, owing to the fact that we have this particular formula regarding relative volatility, it could be the ratio of the pure vapor pressures of the two components. So, if we're going to use that one, that formula, and table number 1, this particular table. Wait, is it table number 1? Okay, it's not table 7.1. It's in my case in here, it's table 11.1-1. I may be referring to the table that is available in McCabe, because the 11.1-1 is the table in Gian Kuplis. So this is taken from Gian Kuplis. But nonetheless, you just have to retrieve the partial pressure of benzene and toluene. Vapor pressure, that is. Vapor pressure, it's not partial pressure, it's vapor pressure. You have your vapor pressure of benzene and toluene at the indicated temperatures 90 and 100. So if you are to get the relative volatility at these two temperatures, you have to get first the vapor pressure from this table and recall the formula that was shared to you regarding relative volatility for systems that are ideal. And since benzene-toluene system is ideal, so we can use the ratio of the pure vapor pressure of the components. So that's why you see here, we simply took the ratio of their pure vapor pressures at the indicated temperature. So this is for toluene in KPA, and this is for benzene. So I'll just pick one. You can go back to this slide later, and you just get the ratio. That's just how simple it is. If the system is not anymore ideal, then the formula that was shared to you will not be anymore applicable. Okay? For sample problem number 2, you are to calculate the vapor and liquid compositions of benzene and toluene for your system, which is at 85 degrees Celsius. We know that for this particular system, Dalton's law apply, and that is the total pressure of the system is the sum of the individual partial pressures. And using Rayos Law, the individual partial pressures, let me just project. The individual partial pressures will be the product of the pure vapor pressure of each of these components at 85 degrees Celsius, read from the table that was shown to you. So I just substituted it in here, and it has to be equated to the atmospheric pressure. So this is what I meant when the problem is silent about the total pressure of the system. Automatically, it should be the atmospheric pressure. And since we only have a two-component system, so your X sub B here would be 1 minus X sub A, because the sum of these two has to be equal to 1. Okay, so you can find now the X sub A. So this is your composition in terms of benzene in the liquid phase, because this is X. It follows that your X sub B will be 0.22. We take this one, we subtract this one from 1. So what is shown in here in the solution is just one component composition, because the other would just be simply taken or subtracted from 1. For determining the mole fraction of benzene A in the gas phase, you can use this particular formula. This is very fundamental, as fundamental since you have it in Chem 1, that mole fraction of a gas or mole fraction of component gas in a mixture is equal to its partial pressure divided by the total pressure of the system. So the partial pressure again will be computed, this time based on the known mole fraction of A in the liquid phase together with its pure vapor pressure taken from the table. So you have this, you have now 0.90 as the mole fraction of benzene in the gas phase. Y sub B then must be 0.1. Okay. Now I will skip again just in case it will not project. You have any questions so far? So what we have here is just a review of the fundamentals of equilibrium, because these things we will be using. There's a need for it to be used in gas absorption and stripping. Any question? So there's none. Okay, so then we will proceed to gas absorption and stripping. But we need to define these two unitary processes before we even go to the fundamentals. So when we speak of gas absorption, it's a unit operation in which soluble components or a soluble component of a gas mixture is dissolved in a liquid. If I will simplify it further, your gas phase in gas absorption has that particular component of interest which your liquid phase needs to take out. So in this case then, the liquid phase is the solvent. It takes out that desired component in the gas phase. So a gas mixture component is being dissolved by the liquid. Now, the inverse of gas absorption is called stripping or desorption. So why is it inverse? Because in the case of stripping or desorption, the component of interest is in the liquid phase, and the transfer will be from the liquid phase to the gas phase. So this time, your solvent, the one that dissolves the liquid component, is the gas phase. So the opposite of the two. So transfer is from gas to liquid for gas absorption. For stripping, it's from liquid to gas. Okay, so stripping involves the transfer of a desired volatile component from liquid mixture into a gas. Now, both absorption and stripping in common with distillation. So if you recall, I mentioned that if I'm done, that I will be discussing in details the types of packing materials, the type of towers in here in gas absorption, because these two processes are comparable in terms of the columns that are used to effect the separation. So it has something in common with distillation because it makes use of a special equipment to bring the gas and liquid phases into intimate contact with the soul, with the objective that a particular desired component is separated from a particular phase. So whichever of the three are we referring to? We take a component from one phase and transfer it into another phase, or separate. As such, it's referred to as separation process. Separate a component from a particular phase using another. Okay, now as for the equipment that is being used, so absorption, stripping, and distillation, again, so the three are mentioned. Operations are usually carried out in vertical cylindrical columns or towers in which devices such as plates or packing elements are placed. So I will show to you the plate column, the packing column, and these packing elements. The same packing elements that are being used in here in gas absorption and stripping, it's the same thing that you'll be using in distillation if your distillation is a packed column. If it's a tray column, then it would be using the trays that will also be covered in here. So the gas and the liquid in these three cases, absorption, stripping, and distillation, flow countercurrent. So they face each other, and the devices serve to provide. So the devices that is being referred to in here is absorption, stripping, and distillation. So these columns serve to provide the contacting and the development of the very important interfacial surface through which mass transfer takes place. So without the formation of the interfacial surface, there won't be any mass transfer. Of course, there has to be driving force, but there is this development of this interfacial surface where mass transfer occurs. Now, in gas absorption, we have problems like the solubility of a particular gas in water. And I have taken this particular formula from the handbook. This allows you to determine the solubility of gas A in water. So as you can see in the formula, it's only dependent on the mole fraction of A in the liquid phase and the molecular weights. Molecular weights of A, whatever A is, whatever gas that is, and water. So that's how we determine the solubility of gas in water. So take note that your solvent here is water. So to give you the example on how we determine the solubility, so in this problem, what is the solubility of CO2 dissolved in water at 293.2 Kelvin when solution is in equilibrium with air at 1 atm pressure? Henry's law constant is given at 1.42 times 10 raised to 3 atmosphere per mole fraction, and mole fraction of CO2 in the gas phase is 0.43. So you are to determine the solubility. So since solubility requires the mole fraction of A, in this case, our A is CO2, CO2 gas. We need to determine X sub A first. That way we can use the formula that was shown to you in the previous slide. Your answer in this case is 736 ppm, parts per million. Now, this is actually a board problem. And actually, these are the choices given in the board problem. And if you look at the choices, you will wonder why, if we come to think of solubility class, so this is what I keep on reminding the fourth year, and now I'm reminding you also, that the board exam does not ask you something so elementary and also provide you choices that are so elementary. If you are asked for solubility, it would have been, in terms of choices, if you're going to ask me, it would have been mole fraction. Because when you speak of solubility, it's mole fraction. You have XA. Okay? But in this case, you are given units that are in parts per million and milligram per liter. So now you may wonder why, how am I going to convert my answer? That way I can choose from among the choices in here the correct answer. So that's what we're going to discuss in the next slide. Okay, so your given information here is the temperature, Henry's law constant, and Y sub A. Okay, so take note of those three. Anyway, it would be shown to you in the slide as well. So let's go to the next slide, which is the solution to this. So if you're going to use Henry's law, we're not going to use Rayos Law because CO2 water system is not ideal. So you're going to use Henry's law, and this is the formula for Henry's law. YA is equal to H prime XA. This is the Henry's law constant, and this is to be divided by, this has been divided by the atmospheric pressure already. Now, in here, you can solve for the mole fraction of CO2. So the mole fraction of CO2 in the liquid phase. And if you look at the units in the numerator and in the denominator, you have mole CO2 divided by total number of moles CO2 and water in your liquid phase. So we need to convert the moles of CO2 to total number of moles to mole ratio. So this is mole fraction, this is small x. You are to convert it to mole ratio. So before you can do that, then you need to, of course, if you have this much of CO2 in 1 mole, in 1 total number of moles, if you take this as 1, then the moles of water would be 1 minus this 3.01 times 10 raised to negative 4. Now, where are we taking it from? We just base it on what we have in here. This is actually to be interpreted as 3.01 times 10 raised to negative 4 divided by 1. So this is your mole CO2 and this is your total number of moles. So if you want the moles of water, you subtract this one from 1. So that is why you have this. But this is still mole fraction. We want the mole ratio. So if it's mole ratio, then that would be the moles of A, moles of CO2 divided by the moles of water. We want to convert from mole fraction to mole ratio. And this is your mole ratio. Now, why convert from mole fraction to mole ratio? It's because in terms of the choices that it's provided in the problem, you don't have mole fractions. So meaning, you cannot stick to this answer of yours, though it is correct. You have to convert it and convert it in such a manner that you will find its equivalent answer among the choices that is provided. So from in here, you'll have the mole ratio of CO2 to water. Now, if you use the molecular weights of CO2 and water, so you have here gram per mole of CO2, you will convert this mole ratio to mass ratio. How would that be? Because you cancel this mole of CO2 and this mole of CO2 here, the mole of water and the mole of water here, giving you a ratio of the mass of the CO2 and water. And that mass ratio is this one. Now, this means that you have 0.0007360 grams of CO2 per 1 gram of water. Per 1 gram of water. Now, if you're going to make this a whole number, so you have 1, 2, 3, 4, 5, 6. That would be equivalent to 736 times 10 raised to negative 6. And what is this times 10 raised to negative 6? That's parts per million. Choices like parts per million, milligram per liter are actually mass ratios. So that's the very purpose why from the original answer that we have, which is also correct, you need to convert to this particular value. the 736 times 10 raised to negative 6. This times 10 raised to negative 6 is the same as saying that this 736 you have divided by 1 million. That is why we call it 736 parts per million, because your denominator is now million. And this is it. Okay? So that's why in your answer, in the choices, it's 736 that you chose. Because after converting the answer of mole fraction of CO2 in the liquid phase, we're able to get this value. Do you have any questions? Okay, I think there's none. So I'll go back to the next to our set of slides. So we go now to equipment selection. So this is just to illustrate this one, the solubility thing. And this is our problem. And the choices and how we work our way or how we find our way to the choices. Okay. Now we go to equipment selection. Now, plate columns, this is already talking about equipment for gas absorption and stripping. Okay, so plate columns may be economically preferable for large-scale operations and are needed when liquid rates are so low that packing would be inadequately wetted. If the packing material for your pack columns are not adequately wetted, there won't be deformation or there won't be the full development of the interfacial surface. They won't be referring to the liquid and the gas phases. They won't be intimately contacted, and as such, there won't be a good separation of what it is to be separated from. So plate towers may have better turn down ratio and are less subject to fouling by solids than pack towers. Now, fouling and turn down ratio. So I would like you to look, I know you know already what fouling is by the term fouling by solids. What about turn down ratio? So that's something for you to look down and check what is turn down ratio. Now for pack columns, so now comparing these two, these are usually chosen for very corrosive materials. For liquids that foam badly, so if there's froth formation or foaming, or for either small or large diameter towers, so pwede gamay, pwede dako, involving very low allowable pressure drops. There is large pressure drop in plate columns, and if you want that avoided, then you use the pack columns. And for small-scale operations, you can also use pack columns in this case. So diameters will be, should be rather, less than 2 feet in this case. Then you can use pack columns. So for corrosive and systems that foam or froth, produce froth, or whether it's a small or large diameter tower in which we only want very low pressure drops, then the pack column is advised to be used. Okay, now how do we schematically represent these two, the gas absorption column and the stripping column or the desorption column? This is how we represent our gas absorption column. Whether we're talking, by the way, class, of gas absorption or stripping, the liquid, take note of this, the liquid is always introduced on top of the column. Whether we talk of gas absorption or stripping, the gas is introduced at the bottom of the column. You see these numbers 1, 2, n minus 1, and n. This is how we number the number of stages. In gas absorption, we number it 1, meaning it's stage 1, where the solvent is introduced. So since your solvent in gas absorption is liquid, number 1 stage or stage number 1 or plate number 1 is the one on top, because it's the other way around with stripping. So again, the way you number your stages for gas absorption is you base it on where the solvent is introduced. And since our solvent is introduced on top, So this is our stage number 1 or plate number 1. And of course, the last stage will be the stage N. Before that, that would be the nth minus 1 stage. Now, the labeling that you see here, I like to emphasize because actually I also emphasize this in the 4th year. Giancouplis has a different manner of representing the phases. McCabe has a different manner of representing the phases. Representing the phases here, class, we only have 2, by the way, the L and the V, but we have 4 streams. 2 streams coming in, this one and this one, and 2 streams leaving your column. And they are labeled based on the stage which they came from. So let's say, for example, for this gas phase, since it's leaving stage 1, it's labeled as B sub 1. And since this solvent is coming from stage 0, because it's still to enter stage 1, that is why it's labeled as L sub 0. This particular solvent now, carrying the desired component from the gas, is labeled as L sub n because it leaves the nth stage. Now, the vapor, which is to be introduced into the column, this is your feed, where you want to separate a component of using the solvent. It's labeled as V sub n plus 1 because it is understood to be coming from the n plus 1 stage, because this is our n. So meaning the next stage to this is n plus 1. So we label this particular vapor phase from that particular stage where it came from. Now, what about McCabe? Now, McCabe only labels it this way: 1 at the bottom and 2 on top. So meaning this is all L2, V2 in McCabe. This is all L1, V1 in McCabe. No LO, no V sub 1, no L sub n, and V sub n plus 1. So meaning the subscripts for the streams in McCabe's are just having only 2 numerals, either 1 or 2. For Giancouplis, it's more specific. So you have each of the subscripts here differing from one another. Okay, that's just how they represent it. So if you're studying McCabe, make sure how McCabe represents its streams. Make sure how it represents parameters and variables in formula. Actually, it's automatic man in all books because other authors may represent a variable or a parameter differently than another one. So you just have to know what the variables in a particular equation represents based on the source. Kung di mo na siya ginkuha ang imong equation. Okay, so that's for our gas absorption schematic diagram. Now let's go to the stripping diagram. So this is our stripping diagram. So still liquid is introduced on top, and this is now your vapor introduced at the bottom. But numbering is from 1 to n. So it's the other way around. Still, we label our streams based on the stage where it came from. So in this case, this gas that is to be introduced into the column is labeled as 0 because it's understood to be coming from stage 0. This one leaves n, so it's V sub n. This one is understood to be leaving from L, or rather from n plus 1. So it's labeled as n plus 1. And this one leaves 1. Okay? In McCabe, this is still 1. This is still 2. This particular representation is based on Giancouplis. Now, do you have any questions so far before I proceed? Okay, so there's none. So then we move on. So that's how we represent our equipments. When we solve problems, it's necessary that you represent them correctly. Now, as for the types of columns, so we know that gas absorption, stripping, and distillation are all unitary processes carried out in cylindrical columns or towers. So this could be any of the 4 in here. So you can have the trade tower, You can have the pack tower or the pack column. So in here you have trays or plates. In here you have packing materials. So the packing materials can either be random or structured packing materials. You can have spray towers. You can have bubble columns. So in here, the gas is bubbled up against the liquid that goes down. In here, you can have the liquid sprayed on top of the vapor that flows upward. So that's the spray tower, and this is the bubble column. And we have this special type of equipment, the centrifugal conductor, where your vapor is still introduced at the bottom and leaves on top, and your liquid is introduced from the top, leaving the bottom. Okay, still, now this time it uses the centrifugal force to separate the component of the gas, the component of interest from it before the gas leaves your centrifugal conductor. So of course it uses this liquid as the solvent. Okay. Now I'd like to show to you the videos from RCHE of the pack column and the tray column. So our tray column actually can either be sieve tray, bubble trays, or valve trays. But when we speak of pack columns, it can either be only pack column using structured packing material or random packing material. So I'll try if this will work. So I'll project this one and let me know if you're seeing the video. If not, then I'll go directly to YouTube where this is taken from. Okay? Just let me know if it will not be shown.
Successfully wala pa play ang video.
Let's look again at it.
Okay, it's not playing. Then I'll share it to you straight from YouTube. Just give me a minute. Okay. Hopefully I'll be able to share it properly and share this column. Let me know if it won't be shown again.
What is a packed column? Let's look again at a cross-flow tray column.
I just have it repeated, guys. So I will share my screen on the seed tray column.
Miss, excuse me, wala sound, miss.
Doesn't have the sound.
Wala, miss. Kanina naman, miss, wala man.
Kaya na wala man sound. Wait. Wala ni ko din-inform. Wait lang.
We got seed trays right here. And what are they is essentially, let me show you right here. You got this.
Wala, gyapon sound, miss.
You see, we edit a lot of
The bubble cap tray was the most used device through the 1940s and early 1950s. An amazing number of them are still in service. The tray consists of a riser with a cap on the top. The vapor flows through the riser and around the cap and contacts the liquid as it flows across the tray. The one unique advantage of the bubble cap is that it provides positive assurance that there will be total vapor-liquid contacting without bypassing of the vapor. Their main drawbacks are due to the complex cap design. The caps present an obstruction to liquid flow, particularly in high liquid-loaded towers. Also, a large fraction of the vapor phase pressure drop is wasted, as it occurs in the reversal area between the riser
Excuse me, miss. Wala naka-share screen.
and mass transfer. The labor
Yes.
Wala siya naka-share screen, miss.
Oh. Kapag. Wait. Do you see it now?
Yes, miss.
Okay.
The bubble cap tray was the most used device through the 1940s and early 1950s. An amazing number of them are still in service. The tray consists of a riser with a cap on the top. The vapor flows through the riser and around the cap and contacts the liquid as it flows across the tray. The one unique advantage of the bubble cap is that it provides positive assurance that there will be total vapor-liquid contacting without bypassing of the vapor. Their main drawbacks are due to the complex cap design. The caps present an obstruction to liquid flow, particularly in high liquid-loaded towers. Also, a large fraction of the vapor phase pressure drop is wasted, as it occurs in the reversal area between the riser and the cap, where it does not enhance the mass transfer. The labor cost of assembling the riser cap units makes these trays more expensive. The weight of these units also leads to support problems on large towers. Consequently, most new applications today are in services where a large amount of vapor must contact a relatively small amount of liquid.
Okay, so main objective of the bubble cap is if you have a large amount of vapor that will be contacted to a small amount of liquid feed. Okay, so, but it's very costly and there's pressure drop that has to be considered. The bubble caps are also, in terms of their intricate design, of course, it has incurred additional cost, okay, because of the bubble cap. Now, I'll show to you another one. Check. Okay, I'll show to you another one. I'll stop sharing. Valve trays. Okay, I hope you can see it already. I just have it enlarged. This one is for the valve trays.
Valve trays, along with sieve trays, have dominated for the last 40 years. Valve trays generally are proprietary and contain movable valve units. When the vapor rate is low, the valve partially closes and minimizes weeping by restricting the liquid flow through the tray holes. At high vapor rates, the valves deflect the vapor flow. This reduces entrainment by creating a weaker vapor jet and results in a greater operation range. The valves do contribute to vapor pressure drop, as the vapor must push the valve open.
Okay, that's for the valve trays. So the valves, as I mentioned there, it goes up and it's being pushed by the vapor. So the degree of the opening of the valves or the degree in which your valves rises up is dependent on the volume of the gas that flows through it. Now, it's a good tray type for you to use when entrainment is an issue. If you want to have negligible entrainment, if not zero, then the valve tray tower is suggested to be used. Okay, so I have shown to you the towers. So we have, I'll go back now to our slides. So I've shown to you the sieve tray tower. I have also shown to you the bubble cap. So the difference of the bubble cap with the valves is that, of course, the bubble cap is comparable to the valve, but it does not have rise and fall. It does not operate in the rise and fall manner because it's already a stationary opening which has a cap on top. It's now the cap that moves as the vapor goes up. So you can listen in detail to the videos that will be that you can review again once this slide is shared to you. Okay, so these are our towers, gas absorption or stripping towers. So they could be packed or tray towers. Now we do material balance in here in our gas absorption and stripping, and we do material balance either on the entire column or in a particular stage. So if our absorption is accomplished through a single stage equipment, then this would be your simple representation of that. This is your liquid solvent L sub O, and this is the liquid that leaves the equipment already. This is your feed B sub 2, And this is the vapor that already has the minimum, if not zero, amount of the component that your liquid solvent take out of it or separated from it. So notice now that we have L sub O and L sub 1 and B sub 2 and B sub 1 in here. The L1, I will emphasize this, the L1 and the V1 are the liquid and vapor phases that are said to be equilibrated, and they are living stage 1. And as such, you have here the subscripts 1. So the phases or the streams that are equilibrated are the streams that leave a particular contacting tray or stage if we have a packed column. So if you would be asked which of the four phases or which of the four streams are equilibrated, that would be this pair of streams that leave a particular stage or that leave your equipment. Okay, and this one is your feed if we talk about gas absorption, and this one is your solvent. Now, when we do material balance, we just consider the streams that enters a particular stage, equate it to the sum of the streams that leave the stage. And we have this M, or we call this the bulk phase M, which is already consisting of the mixture of these L and V phases. Now, if we wish to do component balance aside from total material balance, based on any of our components in our system, then we just need to, I'd like to project this so you would see. We just need to multiply the L and the V phases here by their corresponding mole fractions. So you notice that LO was multiplied to XO, B2 was multiplied to Y2. So we use X for the liquid phases and we use Y for the gas phases. The letters that you see in the subscript before the numbers are actually the component that was used as a basis in balancing. So in this case, this is component. We're using here component C. We call this the C component balance. For the bulk phase M, we use X for its mole fraction and we label it with the subscript C sub M. Now, if you use A, then correspondingly, you have to change also the C's here in the original C component balance to A. But whenever we do material balance class for gas absorption or stripping, we only do one component balance and we pair it with the total material balance. If you make another component balance, it will be of no use because you will just be simply going back to the original equations that you are using. So you only have to use total material balance and one component balance. If you have a two-component system, then if you know already XA, automatically you get to know XB. The example that is written here is for the liquid phase and for a three-component system. Okay, so we have here X again for the liquid and Y for the gas. Now, in gas absorption and stripping, we also have one component balance equation class, an alternative component balance equation that does not use, I'll go back to the original slide, that does not use the entire stream. So in here you could see it's LO, it's V sub 2, it's L sub 1, and V sub 1. Now this may be a challenge if the problem does not give you the complete values of the four streams. So it would be a great challenge because you need to know all four. That way you can use this particular component balance equation. Should there be missing, should there be a particular stream that is not specified in terms of amount, you will have a problem. So there's an alternative equation for you to use. Just in case you won't see this, I'll go back to the next one. This is the equation that you will be using. Now, instead of using LO, V2, L1, V1, in here, you use the L primes and the V primes. And notice that both in the left side and in the right side, you have only two amounts to take note of. that is the L prime only and the V prime. Unlike the original component balance wherein you need all four, LO, L1, V1, and V2. In here, you only need L prime and V prime. What are these L prime and V prime? So L prime and V prime represents the inert amount of your phase. So what's the inert amount of your phase? So in the case of your solvent, the inert amount is always the water that is present in your solvent. In your gas, the inert amount is the air. So you have a mixture of air with a particular gas, and that particular gas component needs to be dissolved in your liquid solvent. So then you will have the V prime as the air only. Okay, that part of your mixture which does not contain, let's say for example, CO2, the gas that you would like to dissolve in your given solvent. If your solvent is pure water class, there are several cases that, or several problems that you will encounter that your solvent is pure water, then the entire thing is your L prime. Because in your solvent, water is the inert part. The other part is, of course, has to be subtracted from the entire part for you to be able to get the, or to be able, for you to be able to substitute only the L prime in this formula. Okay, so take note, you need the L prime and the V primes only, the amount of water and air in your liquid and gas phases. Now, there's another thing that you need to know. If you use this particular equation, you are not anymore multiplying the L primes and the V primes by mole fractions, but rather you are utilizing now mole ratio. This is mole ratio. Why am I saying this is mole ratio? Because in the numerator, you have A. In the denominator, if you subtract A from 1, this is automatically B. So this entire expression tells you that it is the ratio of A to B, the mole ratio of A to B. Now, it's the same thing with the Y's in here. So mole ratio of A to B in the liquid phase, or in the solvent that enters your column, mole ratio of your A in the feed to B. So if you have A and B in your feed, so this is why A, this is why B. Okay, and so on and so forth. So you don't deal with mole fractions now multiplied to the L primes and V primes, but you are using mole ratios. So it's anyway placed in here. So that's something that you need to take note of. Okay. Now, before I go to the sample problem here, with the use of the, for the use of the material balance, I can give you a 10-minute breather. So my time here is 1:43. Do come back, have a break, a screen break for 10 minutes, come back at 1:53. I'll stop sharing now. We'll go back to our slides. So this is our sample problem. Problem number 6. Now a gas mixture at 2.026 times 10 raised to 5 Pascal. Total pressure contains air and sulfur dioxide. Compacted in a single stage equilibrium mixture with pure water at 293 Kelvin. So speaking of pure water, then pure water is your solvent here. And SO2 is the one that is to be removed from air. Now the partial pressure of SO2 in the original gas is 1.52 times 10 raised to 4 Pascal. The inlet gas contains 5.70 total kilogram mole, and the inlet water 2.20 total kilogram mole. The exit gas and the leaving liquid are in equilibrium. Now calculate the amount and composition, or the amounts and composition of the outlet phases. So simply put, we are after the L1 and the V1 and their corresponding composition. So we are to use the equilibrium data from figure 10.2-1. Now, this equilibrium data from figure 10.2-1 simply tells you of the Henry's law constant. Now, this Henry's law constant, which linearizes the relationship, the curved relationship between XA and partial pressure of the gas. This Henry's law constant can be found in the appendix of any of the books that you are using, either McCabe or John Cookle's. And it's also found in section 2 of your handbook. So find the corresponding Henry's law constant based on the system that is given. So in our case here, our system is SO2 and water. So SO2 is the gas that will be removed from air. Now, as to our solution for this problem, it's already in here. That way we can save time. I like to project it so it will appear bigger. So this is our single stage mixer comparable to an absorber, but the only difference is that we don't have a tower or column because this is just but a single stage separation process. Normally the columns are used for multi-stage separation processes wherein a large amount of feed is to be processed. Okay, so if this is a single stage process, our overall material balance, so we need to account for the streams that enters. So that is LO and V2. And we need to account for the streams that leave. The sum of these streams should be equal. Okay? Now, if we will write our component balance based on A, where A is the SO2 gas, which we are interested in, so you just copy, or in terms of pattern, you look up your overall material balance and multiply each of your terms there by the mole fraction of A for the corresponding stream that is presented. So you have your LO XAO, P2 YA2 equated to L1 XA1 plus V1 YA1. We use X for liquid, we use Y for gas mole fractions. We use X for the bulk phase mole fraction. Okay, now these are your two equations. Another alternative equation was the one presented to you, wherein instead of using the total amounts of the streams or phases, you use only the inert portion of these phases or streams. So we'll have L prime, and you have here, instead of XAO, you have the mole ratio. So XAO over 1 XAO. That goes the same thing with the V prime here, and the L prime here, and another V prime here. From equation 1, if you will substitute the given information, this is the total kilogram mole of water that was used, and 5.70 is the total kilogram mole of air SO2 mixture. It has to be equated to the living streams, the L1 and the V1. Both are unknown. But this is equal to 7.90 if you're going to add it, and this entire equation has also the presence of the M, which is equal to the sum of L1 plus V1, which is equal to 7.90. Now, from equation 2, if you will substitute the given, so look at it. So you have LO, this is your water. It does not contain A because it's pure water. The solvent that was used is pure water. It does not have SO2. So that is why you have your 0. Your 5.70, that is your feed, has 0.0750 kilogram mole of SO2 from the given as stated in the problem. And everything here on the right side, I'm referring to the L1 XA1 and the V1 YA1 are all unknowns. Now, since the two equations that we have here have 4 unknowns, so this L1 XA1 and V1 YA1, your algebra tells you that you cannot determine 4 unknowns with just 2 working equations. So that's the time that you consider working on equation 3. So this time you will determine the L prime and the V prime. This is what I've mentioned to you a while ago, that whenever you're using pure solvent, oftentimes water, your L prime is that pure solvent, which is water. So in the case of this problem, it's 2.2. Your V prime is the air in your original gas mixture. So your original gas mixture is 5.70. You multiply it to 1 minus 0.0750. That should give you, oh sorry, I accepted somebody who came in. That should give you 5.2725. So this would be now the L prime and the V prime that you will substitute in here. Okay? The L prime and the V prime that you will substitute in here. And let's see what will be the resulting equation if we do that. Okay? And escape. Now, great class. I have the apprehension that you won't see it. So we're in this part already. So we will determine the YA2, the mole fraction of SO2 in the gas phase. Okay, if you notice, this partial pressure of 1.52 times 10 raised to 4 Pascal, I'd like to go to the problem so you will see. The partial pressure of SO2 in the original gas is 1.52 times 10 raised to 4 Pascal. Now we use the partial pressure, we divide it by the total pressure, which is not, it's here, it's 2.026 times 10 raised to 5. That gives us the initial mole fraction of SO2 in the feed mixture, in the feed gas mixture. So that's the one that you are seeing here. So I will just don't project so I can go back easily from one slide to another. So you have this one, okay? So that's your YA2. Now using Henry's law, now Henry's law tells you that the relationship between the equilibrated streams in terms of their mole fractions would be this. The mole fraction of the gas phase leaving our mixer of A leaving our mixer is equal to the product of Henry's law constant divided by the total pressure of the system times the mole fraction of SO2 in the liquid phase. This is your XA1. Now your YA1 is equal to, so this 29.6 atm per mole fraction is stated already in the problem, if I'm not mistaken. So if it's not stated in here, that's the one that I have mentioned a while ago that you're going to look up from the appendices in your books, or you're going to look it up in section 2 of your handbook, the Henry's law constant for the system that we have in here. So in that case, that Henry's law constant is 29.6 atm per mole fraction. And by the way, class, if you have your Janku, please, and if you're going to look up that particular figure that was mentioned in the problem, the Henry's law constant is right on the equilibrium diagram as written for SO2 water system. Ara to siya nakasulat. So you need not go to the appendix anymore. But if you don't use the diagram, then you have to look for the appendix and get the Henry's law constant for SO2 water system. So that's 29.6 atm per mole fraction. This one, if you're wondering what is this is the total pressure of the system. Why is that? Because your original formula has only the Henry's law constant and XA here. To convert the H to H prime, it needs to be divided by the total pressure of the system. So that is why you're seeing this 2.026 times 10 raised to 5 Pascal. This H over total pressure is the H prime. Okay? And in here, you just have the conversion. You notice that your Henry's law constant has a unit for pressure which is atmosphere, and your total pressure is in terms of Pascal. So we need to make the units agree. So this is just a conversion factor. So now you have a relationship, the very important relationship of YA1 and XA1 given from the Henry's law equation. So you have this. Now, what we did do with this, and with this, and with the v primes and the y primes, you go back to equation 3. Okay, the equation 3 that I was mentioning, so I'd like to post this temporarily. This is the equation 3 that you need to go back to, this one. So in the left side, you will have XAO and YA2, and on the right side, you have all the ones, the subscript ones, because they are referring to the streams that leave your mixer. Okay, so I'll go back to this particular page, and we substitute. So you have here your L prime. Your L prime is your 2.20. That's your solvent, which is pure water. So this is your ratio. So it's 0 because your XAO is 0. This is your V prime, the computed V prime. This is the V prime, 5.2725. So we place it in here. This is the mole fraction of SO2 of A in the gas that enters your mixer. And this is 1 minus this, 0.927. Then in here, you have 2.20 for the L prime representing the L1. And you have your XA1, 1 minus XA1. We don't know this. In here, you have 5.2725, the V prime again. And this is your YA1. Where did we get the YA1? From Henry's law. So what you're doing actually here, class, is you're working on the component balance equation. You're working on the component balance equation together with this equilibrium equation, Henry's law. The goal is you will find XA1. So you find, you notice that you only have one unknown here. The denominator for this one, this is your YA1, so this must be YA2. And since YA2 is 1 minus YA1, so you have 1 minus YA1 in terms of XA1 taken from Henry's law. Now, if I will move down, you have, if you're simplifying this, you will have this one. And you will have two answers. You have two answers here because this will give you, let me clear my markings. You will have two answers for XA1 because this will result to a quadratic equation. Notice that I have your XA1 and beside it I solve for YA1. Now where did I get this YA1? Here. We substitute this XA1 value, the first XA1 value that we got, and substituted it in here. So this is your YA1. You substitute the other XA1 value that you solve from this equation and you substitute it here, and this is your answer. So you go now to the last part, which is validation, the important validation. You cannot process or you cannot accept this last pair. I highlighted in red the YA1 equal to 11.2256 because this should be a value which is less than 1 because this is small fraction. By the fact that it is 11, meaning this XA1 value is not acceptable. The pair that you will use is this pair, XA1 and YA1. So in this case, we have already answered. So we have already answered the composition of the liquid and the vapor leaving our mixer. So we already determined the two unknowns. So we still have to determine the vapor phase V1 and the liquid phase L1 because this is their composition. So kulang pa siya. So how do we determine the L1 and the V1? So we go to the next page. So your V1 is equal to 7.90 minus L1. Where was this taken from? In here. In the overall material balance from equation 1. So V1 is equal to 7.9 minus L1. Okay. So that's the thing that you see here. From equation 2, if you're thinking that you will not anymore be using equation 2, you can now use equation 2 from here because you already know XA1 and YA1. So you can plug in the two values in here and associate L1 and V1 with the equation that you have here in the first, which is also L1 and V1. So you can solve equations 1 and 2 simultaneously with the two remaining unknowns, L1 and V1, since you already have XA1 and YA1 in here. So that's the thing that you're seeing in here. So from equation 2, you substitute the value of XA1 and YA1 and the representation of V1 in terms of L1. And by the way, this should be 7.9. Okay, I have mistyped it class in here. So this should be 7.9 minus L1. In the process, you'll be getting these two values for the L1 and the V1 together with these compositions. Now, these compositions were determined by subtracting. Look at it, it's already B, XB1 and YB1. So we got this by subtracting XA1 from 1 and YA1 from 1. So we get these two values to complete the required information, which is the composition of the streams leaving the mixer. So if you go back to the problem, calculate the amounts and composition of the outlet phases. So the outlet phases that's referred to in here is this, the amounts of these two and their corresponding compositions. So that's the compositions that you have seen in this page here and in this page. Okay? Do you have any questions? This is single stage absorption, gas absorption. We have a single stage. We haven't yet reached multi-stage process, and that would be our discussion after your exam. Do you have any questions? I'll stop sharing now.